He is BTech in Physical Sciences from Indian Institute of Space Science and Technology, Trivandrum, in the year 2011. Currently, he is working as a scientist at URSC, Bangalore. His research interests are space physics, high energy space instrumentation, heliophysics, solar planetary interaction, space weather, etc. He has worked on geostationary radiation spectrometer on board GSAT-19 and a class payload on Chandrayaan-2 and Helios and magnetometer on Aditya L1. So he has several publications in these areas. So with this introduction, I invite the speaker to deliver his presentation. Yeah.
Yeah, thank you, sir.
Over to you.
Thank you for the introduction. So good afternoon. I'm Srikant. And today I'll be giving this presentation on the topic of space qualification and environment. I hope my slide is visible and it's in full screen and I'm audible. If someone acknowledges
visible.
that.
Yeah.
Sure. Thank you so much. So, so I have designed the outline of the talk like so. So in the next half an hour or so, I will try to give you a flavor, an overall flavor for what the kind of space environment is and what sort of measures one has to take in terms of putting systems up in space that will work reliably, and what measures we need to take in terms of that. That essentially entails the part of qualification, and what other effects space systems will have when, let's say, a spacecraft is put into space. So I'll give you a flavor of things from an overall perspective, and that's how I've planned. So initially we'll start with what is space environment, just the introductory introductions, and then what and who controls it. So and then go to what are the effects mainly over a planetary scale, and what are the space weather effects and the space environment effects, and then if particularly for spacecraft systems, how can they alter the functionality or modify the functionality or being harmful to those. So in that perspective we will talk, and then come to the space qualification measures that usually we do, and then give a conclusion. So then let's move on with the talk without any delay. So what is the space environment? So I'll split those into two smaller words. I mean, I have used space and then some easier word that we can all understand, which is weather. So coming to the second part, we know that weather is kind of a word where we'll try to understand how our environment works. So if someone asks you what is weather today, how is the weather today? It's hot or humid or rainy or something. So we will know how the local conditions of pressure, temperature, and precipitation are, and then that is summed up into the word weather. But so for a space kind of an environment, such a thing exist or not? Yes, it does. So where we may be having some idea that space would be almost empty, and then we will not be able to see anything, um, especially from the perspective of uh, rain, clouds, or anything. So such things won't be there. So the terrestrial word weather, where we associate ourselves with our local climatic systems, is quite different to what we term as the space weather. And space weather is essentially that which holds the space environment mostly, and that is what drives the total essential part of the space environment. So what it contains. So here I am trying to give you a flavor of what sort of things that one can expect if you go to some a location where we call it as space. Basically, above the Kármán line, above maybe a few hundred kilometers above the surface of the Earth, we can say that yes, we are into the space. And from there, what it essentially entails. Here I am giving you a very artistic view of the heliosphere itself. The center of the planet, center is the sun, and then as a sun plows through the galaxy, we see that there is a huge shock formation, and then essentially there's a lot of plasma and magnetic field environment that exists. So that part is called heliosphere, and that heliosphere is the entity in which we all understand as this space that we know of. We are not going beyond the solar system for this current talk, so we are restricting ourselves to the heliospheric extent, and where much of it is vacuum, and the thermal extremes. If there is a surface or if there's a body there. So I'll come to that part. So there can be huge temperature extremes, and how and why we'll discuss much more. And there's huge fluxes of solar radiation particles, and then in terms of electromagnetic radiation, energetic particle radiation, in terms of protons and neutrons, protons and electrons, and so on. And there is something called galactic cosmic rays, and there are micrometeorites, and then because of the man-made activity, solar space activity, we do expect a lot of orbital debris. So this is what kind of space environment we can expect or envisage when we are talking about let's say space systems as such. So who controls it? Of course, now the prime mover for all of this space environment is the sun, because as I have shown in the previous slide, the sun is the nearest star that holds our solar system, and its effects are the ones that permeate into the heliosphere. So, and much of the effects that we see in terms of space environment are associated and can be associated to the sun. So in what ways? In different multitudes of ways we can have these effects of sun, and one of the ways is through solar flares, where these are very high intense explosions, sudden explosions of energy, as you can see in this photo. So this electromagnetic radiation output rate, imagine like huge kinds of huge bomb blasts that can happen with extreme explosions of energy. So we can see that the light that is emitted, mainly the electromagnetic radiation spanning from radio up till gamma rays, can be seen once there are solar flares. So huge flux of solar flares can come all of a sudden. These are transients, by the way. So it's like a hailstorm. All of a sudden you'll see that the weather is calm, and then suddenly there would be a hailstorm, and then that's it. So such events are called transients, and solar flares are one of those phenomena where we can expect these transient events where very high energy electromagnetic radiation is given out of the sun. So how it impacts the planetary scale atmospheres or exospheres of the planets per se is that they will ionize the atmosphere and cause the ionosphere to have a lot of changes. So in that sense, our communications and all can get disrupted. So solar flares are one of those to keep an eye on, one of the solar transients that we'll keep an eye on. And it is one of all the space agencies have detectors and systems in place to record these solar flares whenever they're occurring. So apart from the solar flares, there's also something called coronal mass ejections. So sun affects through all these kinds of transients. Again, this is a transient where there's a huge plasma blob, as you can see. This is a picture taken from LASCO, an instrument called LASCO, and it's a coronagraph. Imagine that there's a disk blocking out the sun's disk, and then you'll see the emission if there's a huge plasma blob coming out. I hope you can see my cursor. And when it happens, this emissions can reach into the heliosphere and then pass through the planetary atmospheres, and then can disrupt the geomagnetospheres or planetary magnetospheres if they are present. If in cases such as moon, if you're standing on moon, let's say, and there's a CME that's passing through it, you would feel that there would be a huge plasma cloud with magnetized plasma cloud that's passing through it, and then so that you are totally exposed to all the radiation, high energy particulate radiation that permeates the local lunar environment. So, but Earth is sort of shielded due to its geomagnetosphere. So when you say space environment, it depends on where you're located. So at each point in space may have a different local space environment. Just as I mentioned, how it is different when you're in a low Earth orbit around Earth compared to a lunar orbit or on the surface of the moon. So coronal mass ejections are one of those other transient features which one can expect to alter the space environment in terms of its magnetic and plasma output. Then how they're propagating. So as I mentioned, how they propagate. So the previous one was a remotely sensed observation through remote sensing instruments. But then if you are to measure them in situ, or at some point in the heliosphere where you're standing somewhere in the heliosphere, so placing yourself, then you can see that these are huge plasma clouds, got sort of features with proper shock formations and then turbulent sheath formations as they push a lot of plasma material and accelerate it as into the heliosphere. So this is how one can envisage that it is some a kind of a huge plasma bubble that's pushing through, and then you will feel that there is sudden spikes in transients of plasma density and then magnetic field variations as we feel the propagation of a CME. So these are again some of the important features that can alter the state of the space environment for up to a scale of few days. So the one thing that I didn't mention that about flares is that flares actually last for maybe a few minutes to hour scale. So those are the transient time scales. But then CMEs associated with the particulate events, once they start to emit from the sun, they propagate over a few days depending on their mean velocity, and then their effect can be seen or observed up till for a few days time, at least 2 to 3 days time. So that's where the change happens in the time scales. And then as part of the solar flares and solar radiation storms, solar coronal mass ejections, what we can also expect is solar radiation storms. Apologies for this picture not so having been so clear, but what I wanted to depict from it is it's a huge plasma energized particulate population. Now it is no longer just plasma; it is accelerated towards very high energies, kilo electron volts and even mega electron volts, and at times up to giga electron volts. To those energies, these are accelerated, and then when we are placed somewhere, let's say in the Earth's orbit or outside the Earth's orbit for any spacecraft, that will go through these solar radiation storms, essentially triggered by the solar events like solar flares and CMEs. So these are associated events, not direct events. So in all these ways, we can see that these are the transient phenomena where we can expect that there are changes in the space environment. Apart from this, if you are linking yourselves or associating yourselves to some kind of a space within the Earth's magnetosphere, here I'm showing you a picture of the Earth's magnetosphere, and much of our spacecraft systems are located in and around this space. So there is the low Earth orbit happens to be very close to the inside the inner radiation belt, and then the geostationary orbit happens to be at the in the outer radiation belt. So if this for such spacecrafts, what kinds of transient phenomena that are there, we have already discussed. So whenever there is solar activity like flares or CMEs, we would see the effect or response of those through the modulation of the solar magnetosphere. But when there is no transient from sun, let's say the sun is quiet, the solar activity is quite benign, then if someone asks, oh, how is the solar environment today? So then in that condition also, some features called Earth's radiation belts. These are permanent populations of energetic particles as shown in this. So the red band there, you can imagine that once you extend these into the 3D, they form kind of a toroid. So these two tori form the Earth's radiation belt. One is called the inner belt and the outer belt, separated by a slot region, and they actually form the very high energy radiation regions that at times the spacecraft may have to go through. So this is where mostly these consist of protons and electrons, which are accelerated and then they permanently stay there. So somehow it is that the geomagnetic activity is such that there is always a residual population of these plasma, these energized particles. And one of the features that one can see is that because of the lopsidedness and asymmetry of the Earth's magnetosphere, we can see that yes, one of the belts, and these belts happen to taper or come into the in the lower altitudes onto a region called South Atlantic anomaly. You can see maybe somewhere here or so, where towards the South Atlantic region there is a lot of flux of these particles coming in. So that for low Earth orbits, that region happens to be a radiation dense zone, and it's sort of really hazardous for any of the space assets or even for astronauts. So even if there is no solar activity, we can say that the Earth's magnetosphere itself hosts a really high radiation environment in these parts. So maybe if you go out to some of these locations which are in the polar orbits, if you select let's say a very high polar elliptical orbit for a spacecraft, maybe for to a greater extent of the orbit, you will see that the environment is quite low, and that by low in the sense it would mostly be dominated by the solar wind and low energy plasma. But once you go towards these belt regions, solar radiation, they are also called Van Allen belt, named after the scientists who identified them. And so these are one of the persistent radiation regions that we can think of. So apart from this, let me go to this slide and then show that there is also another source of radiation that can alter that permeates the space environment. Those are the cosmic rays. So cosmic rays are those very high energy particles. Again, these are charged particles, mainly constituting of protons, electrons, and heavy nuclei. And when they are known to be galactic and extragalactic origin. So they are not coming from anywhere close to our solar system. I mean, they are not generated within our solar system. They are coming from phenomena which are really high energy phenomena that are happening in the extragalactic space, mainly due to, you would have heard of let's say compact objects, mainly in terms of black holes or AGNs or so neutron stars. So I would not go to the details of those because they are out of scope of this lecture. Maybe someone else may talk about that. But definitely, what I can say that the cosmic rays origin are out of the solar system, and they come almost from all directions because there are several galaxies located around us. So it is considered to be a near isotropic source where very high energy particles, even gigaelectron volts and beyond, try and permeate into the Earth's geospace. And when they interact with the Earth's atmosphere, so this is a simulation that I'm showing on this plot, where once the particle comes in, because of the atmospheric interactions, interaction with the atmospheric neutrals, it will generate a lot of nuclear secondaries because of the nuclear interactions it happens with these very high energy particles. So the GCR atmospheric interaction generates a huge cascade of particles which can be of different types: electrons, protons, muons, and then even neutrons. So we can capture some of them even on the surface because in terms of muons. So the space environment is full of these as a result, because it not only generates the cascade into the Earth surface, towards the Earth surface, but away from the Earth surface also. So on the whole, if you see if you're in an orbit around the Earth or somewhere, you'll see that the effect of or the remnant of these cosmic ray interactions in the Earth's atmosphere, or for that matter, any planetary atmosphere if it's there. So this is always there, and this slightly gets modulated with the solar activity. So it is known that solar activity and cosmic ray flux is anti-correlated, but nevertheless, cosmic rays and the solar Earth's radiation belts constitute a near static background, while the transients like solar wind, high energy solar wind, and solar flares and CMEs form the transient background, the transient regions for the solar environment, the Earth's, the space environment. So let me come back to this summaries slide on showing you what sort of effects one can have. So how sun affects the space environment, or here the term that's used in scientific parlance is called space weather. So space weather is that which tells us what's currently happening in terms of whether there's this flare or not, or what is the kind of plasma output that's happening. So if you want to know something in terms of the space environment, we use the term space weather. And so space weather constitutes of everything that I'm showing you in this plot, where from solar flares to coronal holes to sunspots. I've not dealt much about the coronal holes and sunspot features, but nevertheless, these are all related to the sun, where what we are interested in are the transient as well as the near static outputs, both in terms of electromagnetic and plasma outputs that can affect a geomagnetic system like that of the Earth so they can create aurora and they can perturb the ionospheric currents and then change the total electron content of the ionosphere and cause something called ionospheric scintillations, where it can alter the effectiveness of our communication systems. And also they can generate huge ground induced currents. So they can, this will be very these are all detrimental effects, of course, except the aurora, which we are known to have a it's known to be beautiful, and then we enjoy those seeing them. They're the aesthetic in nature, but definitely these are all the geomagnetic responses of the solar inputs. So with all this, this is what I wanted to show in terms of the harmful side effects of all those space environments induced by sun, essentially. So what are the space weather's harmful effects, especially for our space assets? So if you are in we will see that there will be a lot of this plasma hitting the satellite, so there can be something called surface and interior charging due to these particles, which are wherever they are, either they are in the radiation belts or due to GCRs, galactic cosmic rays, or even solar particles, and so on. And when they hit the external surfaces of these the spacecraft, they can cause a lot of surface charging, and they can in fact degrade some of the systems, especially the solar panels. And nevertheless, it's not just that, but there will be a lot of other effects that I'm showing you in this plot. So it's a good summary plot to show that captures several of these effects, so that we are to be wary about. It can also affect the airline passengers, especially to the polar routes, where it can be huge flux of particles that going through, and it can also alter the Earth's magnetic Earth's density in terms of not the Earth's geospace density, because there's a huge influx of plasma that can increase the drag. And you would have heard that several spacecrafts have been lost because of the increase in the atmospheric drag in the low Earth orbits, especially. And I mentioned about the ionospheric currents that are generated, and then there can be solar radio bursts that can interfere with the communication systems, and also the disruption of the telecommunication cables due to huge GICs, ground-induced currents, and that can affect our infrastructure as a whole. And that is something that so we are to be wary about, just like how we are having huge systems on ground to understand the weather and monitor it and then even predict it. We do have systems in place, or at least for most space agencies, concentrate on monitoring, understanding, assessing, and trying to predict the effects of what is happening in the space environment, so that we can maybe try and protect our space assets. So what do space agencies do? This comes to the second part of our of the lecture, where to attack or to try and tackle the problem that happens in the space environment. So it's a very harsh environment, I would say. So what do space agencies like ISRO do? So they design and develop spacecraft and subsystems that are not so susceptible. So they are sort of robust, and avoid such regions of, so we would not want to do operations, especially very sensitive operations, during high radiation regions. If you're going through, let's say, solar, like South Atlantic anomaly, or during radiation storm in the core of the Van Allen belts. So we would not want to do such operations, is something that space agencies do. And of course, as from a monitoring perspective, we do monitor this kind of space radiation by hosting dedicated radiation sensors on board our satellite. And finally, the part that we want to highlight is we want to qualify our components or our each subsystem, everything that we put on our spacecrafts for space usage. So what do we mean by that qualification? We'll see in the subsequent slides. So this is the sort of the summary from that I can put together in terms of space environment, how it can get affected, how a spacecraft or a space asset can get affected, and how different it will be from its functioning when it is tested on ground. So as I said, in space there would be, we are almost looking at vacuum. It's a very high it's very high degree of vacuum, that at least in beyond 10 per minus 12 or even 15 millibar. So we can not get easily such kinds of vacuum on ground. So we have very high vacuum system, ultra high vacuum systems available, but replicating space is a very tough task. So what it entails, the effects are such that you know that there can be certain materials that can outgas. So because once the temperatures are high enough and then the vacuum is good enough, then you can expect that there are some trapped gases. So outgassing is that phenomena where there's leakage of unwanted leakage of trapped gases into the ambient, and then they can deposit, those trapped gases can get in deposit on sensitive systems like sensors or optics, and then degrade the functionality. And then other problem with vacuum is that there's no convection that can happen. So convective heat transfer, because there's no material medium as such, so no convection. So we have to think of alternate means to maintain the thermal aspect. So which comes to the second part. And as I said, if you place towards the sun side, an exposed surface can reach up to very high temperatures, because the solar radiation and there's no way as such for the heat to go away. But on the shadow regions can, if they are in the shadow for long, they look at deep space and they can have very reduced temperatures of up to minus 150. So this is not, and these are not hard numbers. This is just to give you a flavor of what kind of ranges we are looking at. So obviously there's a large temperature gradient across in the system and across spacecrafts, if you say. So what is essentially done, and very important thing that's done, is thermal control on the spacecraft and for each subsystem. So we thermal engineers developed and employ different methods to regulate the temperature of each subsystem or each component in the way it is desired to be operated. And for that they use different kinds of engineering techniques. One of these is, as I've shown you in the small picture, is this MLI, multi-layer insulation. That golden colored cover that you would see, the envelope that you would see on the spacecraft. If you would have ever seen any photographs of the spacecraft. So that will give you sort of an insulating layer where it will reflect off several of these solar radiations, and then trap the heat if needed. And then if you want to increase the heat somewhere, the employment of heaters, then to have radiators that will radiate off the heat to cool the temperatures, to have the reduced temperature. So thermal management in space to maintain the desired temperatures is a huge task, and that is something that is done for all spacecraft and space assets, and it is essential. And sorry. So the third part is already something that we have talked about in detail about the radiation itself. It essentially entails not just the electromagnetic radiation coming from sun, but all these transients that we have talked about. And also, even if there is nothing coming from sun, there are these radiation belts, South Atlantic anomaly, which are actually a hazard for not just the electronics, but also for any of the um, uh, astronauts, which is basically human activity in space. And then the fourth one is in the space environment that entails the space environment is the debris. So the micrometeorites, there are several micrometeorites which are remnants of, let's say, the comets or asteroids. Then that will spew off everywhere into the heliosphere, and they have very high velocities, hyper velocities that in the orders of tens of kilometers per second, and they are very small in nature. As the name suggests, they are in micron size up to millimeter size, and then there's like very high velocity tiny projectiles, and then they can impact the situation, the impact the structures of the spacecraft, in the sense that it's like coming and there's a missile coming and hit, which is a micro missile. And then this, because of these all the space activity, we have experienced um, several of these orbital debris from our older missions, spacecraft or remnants of it. So there can always be a situation where we can probably be expecting that there could be some old debris that would be there, and we want to avoid those. So what is done is that space situational awareness is essential, where we continuously monitor all these extraterrestrial objects that are there and the trajectories, and then see if they are harmful or hazardous to our space assets, essentially our spacecraft and other systems. So all of it entails, all of this in the, I think this summary slide should entail what is essential or what is needed to tackle the space environment. So for that, we have to go for something called space qualification. every subsystem or every spacecraft, every space asset that we put in requires that its hardware can survive both the launch and as well as the space environment. Now you know that what entails a space environment. It also there are several rigors that will have to go through the launch because of the shock and then the vibration. So the launch itself is a huge takes a huge toll on the subsystems. So we have to ensure that the hardware survives that. How do we do that? So we do very rigorous testing before flight, and what sort of testings one can do, and that essentially qualify. I mean, essentially happens to be the part of qualification measure, and that increases the mission's reliability. So how it functions, the functioning of the space asset or spacecraft, whether it is in the intended way or not, and for the time it is expected to perform. So those parts are essentially the reliability aspects. So by rigorous testing and understanding the system, we will make sure that the design and all the design and engineering is done essentially caters to the reliability aspect. And of course, as I said, it will depend on the kind of mission because it is very local. If same kind of space environment won't be there for a LEO and a GEO or a MEO orbit, or for that matter, interplanetary mission. So each mission has its own type of space environment, both in terms of static and dynamic natures. So one has to account for the type of the mission when you're looking at the um, how we are to qualify a hardware in space. So here in the next few slides, I'll try to give you some view of understanding of how the space qualification tests are, what it entails. So all of these material is available online. So you can find out. So it is from the freely existing literature. So these are the tests mainly to survive the temperature variations and then the vacuum condition. The main thing, one test that we do is called thermo vacuum test or thermal vacuum testing. In the plot, you can see that the entire spacecraft is kept into a huge chamber, which will be evacuated, and then we kept uh, at some temperature ranges. And it's not just temperature ranges. One thing I failed to mention is that there's as a spacecraft passes through the sun, into the sun and out into the shadow based on the Earth's shadow, there will be huge changes in the illumination. And as the solar illumination levels change, there will be huge temperature changes. So it is like going into huge Antarctic winter, and the next in some few minutes coming to Sahara Desert. So because of that, there will be the system will undergo thermal fatigue. So one has to make sure by this thermo vacuum testing, what we ensure is that all the systems are robust enough to withstand those temperature changes, and also in the vacuum condition. So they're able to radiate out the heat whenever they need to, and then still maintain the structural integrity, and so on. So this test is essentially done. It's a huge test that it will go on for weeks for each satellite, and it's also done at subsystem level. And this essentially qualifies. It's essentially one of the main qualification tests for space. And the second one is maybe the mechanical aspect. As I said, that there are a lot of loads that the mechanical loads that the spacecraft will have to take during the launch. So for that, we do vibration and shock testing. Here it's shown that in the picture we are showing is a spacecraft mounted on a vibration fixture, and it will be vibrating the way based on the levels that we expect. And then, as I mentioned, this huge radiation that will happen, all types of radiation that I don't want to repeat that. But whenever there is a high energy particle radiation happens to pass through our sensitive electronic systems, we will see that they do deposit a lot of charge into its active medium. And due to that, there can be what we call as the radiation dose damage into the detector systems, or let's say semiconductor systems or so, because most of our electronics is based on semiconductors, and they are very much susceptible to these incoming particle radiation. So what we do is to take these at different components, all the electronic components, and then try and qualify them to certain levels of radiation on ground. So we expose them to different types of radiation, be it protons or gamma or whatever that we expect in the orbit, and then make sure that these kinds of effects. So one of these is called, they are called single event effects. Single event effects. So there can be an upset if it's a digital system, that there can be a bit flip, and then that will cause that is not intended, but these are undesired effects that are caused due to the very high energy particle radiation passing through the semiconductor digital systems. So single event effects and single event upsets are some of these testings that one has to see, and then see for a given set of and flux of radiation or effluence of radiation, what is the maximum number of times, or how robust is the system for single event effects. Such things are done as part of the radiation qualification of the space electronics. So essentially these four, I mean, would cover the major aspects of the qualification of a system. There are several other testings and then qualification measures, but they are more related to each, is very specific to the it's a subsystem or a spacecraft, but these are the overall ones that I wanted to mention. Then coming to the challenges for spacecraft, for astronauts, now that we know that India is gearing up for human-based missions, mainly sending astronauts into space. So we have to be wary about, till now we talked about space assets as just spacecrafts or electronics or subsystems. Now we want to look at humans in space. Then there are several challenges when you put yourself in space. One is the microgravity, the loss of as you go further away from Earth, the effect, it won't be zero gravity, it's called microgravity, and those effects will have a telling effect on the muscles and bones, and so they can weaken them. So these are some of the things that astronaut training entails. And exposure to these solar and cosmic radiations, all these radiation types that you've talked about, can pass through the shelters, or rather the crew modules or the astronaut ISS modules, if they're there. Rather, if in our case, there would be the future Gaganyaan and then the Antariksha station modules, wherever they're there. So we have to make sure that the astronauts are well shielded, and then they don't have a high exposure to these solar and cosmic radiation. So we have to monitor them. As I said, we need to monitor the space situation in terms of space environment, and then take adequate measures to shield the structure so that the very high levels of radiation are not seen either by the electronics, onboard electronics, or by the astronauts. Then, of course, the astronauts will have to live in a confined environment. So it results in psychological stress. So one has to train for it adequately before moving to space. Then, I mean, there won't be a huge crew once they're in space. So the extent of medical support that one can have during these missions is quite limited. So these are some of the things apart from the well-known challenges. These are some of the things that I wanted to highlight when we are coming to the human-based missions. So key takeaways. This is my concluding slide, where I want to say that yes, we understand that the space environment includes different types of entities, or different types of elements, essentially the vacuum element, the radiation element, the high temperature extreme element, and so on. And all of them have to be folded in when we are designing a spacecraft. And then very extensive testing measures are to be taken to ensure hardware reliability. Otherwise, there won't be, we can't reliably say that yes, the system performance is good enough and then as per the requirement. And that is why understanding the space environment happens to be a fundamental tenet to a feature to the space engineering. Yeah, thank you.
Thank you, Srikant, for finishing well in time and for the very elegant lecture you gave.
Yeah,
before I see the question from the audience, I would like to ask one thing.
Yes, sir.
You said some mechanical vibration testing and all that. Is it under atmospheric pressure you are conducting or in vacuum?
The vibration test is usually done in air only.
Air only.
So
Okay.
in air. So only yeah, because here we are looking at the launch condition. So the launch as it happens on ground, so we will not have the launch effects will not have the launch effects in vacuum. So when we do the testing, it is also done to emulate the same condition. So it is done in air. The thermovacuum is only for the thermal cycling and then the vacuum and testing of the subsystems.
Okay, thank you. Let
Yeah.
me see the questions.
Okay.
So there is one question.
Okay.
With increasing space missions and satellite launches, how will space debris affect future spacecraft design and qualification process?
Okay. So again, it depends on the orbit and also the size of the spacecraft. So maybe what I can say is that one thing is more debris. We have to be more. First thing is more aware of that there is debris, and then we have to keep an eye on in terms of the space situational awareness. And second thing, maybe if we can go for a bit more. It depends again on the satellite size because controlling and maneuverability of the satellite also depends on the satellite design itself. Maybe my next speaker will enlighten us much better than what I will be saying. But how we maneuver in terms of a very detrimental situation depends upon several factors, depending on how much the debris is and how much what densities the debris can be, and all those. So definitely from a design perspective, I think the question was from a design perspective. So maybe agility of the spacecraft and also the feedback to the spacecraft that maybe that there is in fact an inclement situation there where you can have probably a collision in the with the debris. So all of these have to be included, when we are planning a mission, and then probably yeah, I think Srikant sir has a hand raised. Maybe he wants to say something.
Yes, Srikant sir.
Okay.
Okay, there are some more questions which are more advanced.
Yeah, please.
I believe can be taken up later. Yeah, with
Yeah.
this, I thank you very much for your talk. And before going to the next speaker, let me introduce Srikant sir.
Yeah.
Yeah, Srikant sir is currently division head MPAD-1 SSEG and mission director Chandrayaan 3 and Aditya L1. He has got his MSc and MTech degrees from Andhra University and Devi Elia Vishwavidyalaya. And he is a recipient of Rashtriya Vigyan Puraskar 2024 Team Award Chandrayaan 3, ISRO Young Scientist Award year 2012, ASI Team Achievement Award year 2013, MOM Mission Operations. So with this brief introduction, let us listen to Srikant sir's talk. Over to you, Srikant.
Sir, good evening. Will you hear me, sir? Hello? Hello?
Yes, sir. We are able to hear you.
Yeah, sir. Good afternoon, sir.
And share your presentation.
Yeah, please, sir. Madam, I'm presenting, madam. Yeah. Sir, you want me to share or you are sharing, sir?
No, I don't have your presentation. You
Okay,
can you not share from your end?
Yeah, I'll share it, sir. Now.
Share the full screen.
Yeah. afternoon all. Actually, thank you for the introduction, sir. And it was an earlier presentation from Srikant and other team is very interesting because how the spacecrafts in orbit are going to face the sun's heat and your debris effects on the satellite management is a very big exhaustive topic. Anyhow, I'll try to address few aspects in my presentation. Coming to the first point is agenda wise, it was only given that orbital dynamics, but I try to see that for the audience purpose, I try to see that I incorporate along with the orbital aspects, the overall mission complexity, how it is there and how that is achieved over time. I want to give a brief overview for all the participants. When you say mission planning is a complex and multidisciplinary activity which starts from where? First, it starts from the definition of the mission. If the satellite, somebody says that I want an imaging payload, and he says that this is my resolution, this is my swath. Either he defines, a user defines, or else somebody says that I want to put this satellite at L2, Sun Earth L2, Sun Earth L1. Somebody says this satellite has to go for around Mars. Either different objectives are defined based on the requirement. Then, based on the objective, how the orbit is selected, what are the criteria followed, I'll be covering the slides. Then design of satellite to accomplish the mission, that is very much important. Relation of the satellite, launch and operation of the satellite, and till the end of mission of life. So requirements translates to relation, execution, implementation, and launching the satellite and meeting all the requirements. And also once the satellite reaches the end of life with respect to the criteria defined for the with respect to fuel or wear and tear of the systems, all the things considering, we have to declare the end of life, and we should also see that satellite is not becoming debris. We have some strategy for some sorts of satellites, whether it is in low Earth orbit, we will try to use the fuel water leftover and re-enter into the atmosphere. Otherwise, if it's a geo orbit, we'll try to push into the graveyard. Like that, we have some sort of strategy which has followed by every satellite with respect to the management of the debris from our side. But all other contemporary space engines also trying to follow that. But still, the satellite is not operational and is not able to do anything. It has lost all the elements and all. That becomes a dead object for us. Coming to the types of mission and orbits, as we see, there are different types of orbits like low Earth orbit, medium Earth orbits. Then it is classified into categorized into polar orbit, inclined, and a constellation. It might be a single satellite. It can be multiple satellites in different orbital planes and different phasings, different local times. I'll be covering that. And geostationary orbits, then interplanetary missions. Now, all these categorization of the satellites also is categorized. These are types of orbits, but categorization of these satellites is done basically with respect to weight and the power also. Is a general categorization. Like nano satellites are there which weigh from 1 to 10 kg, and hardly the total power is required with 10 watts. Micro satellites 10 to 100 kg where we require 100 watts. Small satellites 100 kg to 500 kg where we require a kilowatt of power to manage the such systems. Large satellites above we're having 500 kg to 5 ton, so it is more than 1 kilowatt. So these are very coarse level of categorization of the satellites based on their mass and the power, what is required to manage the mission. Coming to the typical mission elements, it starts from where? As I told you that initially the object is defined, then realization, testing, implementation, everything is done on ground. Then what happens? The launch happens. After launch, we get to the satellite into the orbit. Then we do the space. Then we do the space segment definition, what is defined on ground earlier to before launch. Then we do the mission operations. Then we using ground segment, we'll do the reception of the payload data on ground. Satellite health monitoring we carry out. Then data processing is done. Then user requirement of if it's an imaging payload, like this image is generated. So this is a typical mission sequence which works for all satellites based on with there may be small changes based on the objective of the mission. These are overall things if you see. Coming to the as I explained you now, this is another view of seeing the mission goals, mission requirements for launch vehicle. See, when it's a launch vehicle, the mass of the satellite also decides, and orbit what would reach also decides whether you have to use a what type of launch launch vehicle, whether it is SSLV or we have to use our PSLV or GSLV or LVM. Depends on the mass of the satellite and our orbit. Then further corresponding space segment, we say payload plus mainframe. Then it comes under orbit, what I defined. Then attitude, the orientation of the satellite. This plays an important role because once we have put the satellite in the orbit, now satellite here has to be in particular orientation. One is that orientation should be conducive for us to support the communication with Earth and also generate power by using solar arrays, as well as we should be able to operate payloads. Like the actual definition itself is orientation of satellite also decides all these aspects. As a ground segment, we have to define what is the stations required for receiving the data, then mission life, how much it is. Then if you see under orbit, we have one under platform, we have structure. That is our structure which takes care, then power, then attitude orbit control system, then thrust RCS propulsion system, telemetry and telecommand system, thermal system, and sensors. So all these systems, I have only listed few major systems. All these systems together forms a platform, and along with the platform, payload flies, and this is how the space segment is defined. Now the applications. Now we understood how the orbits are there. Now when we see with respect to altitude of the satellite, low Earth orbit can be from 250 to 1000 kilometers. Majorly the applications are Earth imaging, reconnaissance, space shuttle, astronomy. These are some sort of applications which we majorly use. Then MEO orbits, that is from 1000 kilometers to 20,000 kilometers. This is also used for Earth imaging, communications, navigation, and astronomy. As well as for high altitude orbits are 20,000 and above. They are used majorly communication, astronomy related, sun related studies, navigation. The hyperbolic orbits are majorly for interplanetary missions. So you can see the classification, how slowly the from the types of orbits to the applications of the orbits, for which application, which type of orbit is required, is a categorization here, which you are seeing here. Now coming to the types of orbits, when you say we are having, when you say here geostationary orbit is one thing, and geosynchronous orbits are 24 orbit period. Then some useful functional orbits, there are multiple types of orbits, but majorly we use for applications purpose of imaging sun synchronous orbits. Critical inclined orbits we don't use, but they are used by Russians. This is a 63-degree inclination where the apogee is fixed over their region, so that maximum time of the satellite spends over the region for their purpose. And highly eccentric orbits, which are 12 hours, and intermediate transfer orbits, interplanetary orbits. So these are some useful orbits which normally all of us use it. So under that we have equatorial, means inclination of the orbit is 0 or 180 degrees. Prograde orbit means it is inclination between 0 to 90. Then polar orbit exactly inclination is 90 degrees. Retrograde is between 90 to 180. This is how the orbit classification done based on inclination. So coming to geosynchronous orbits, as I told you, the orbit with the same Earth rotation rate, orbit with 24 hours is called geosynchronous orbit. And geosynchronous orbit with an inclination of 0 degrees is geostationary, because satellite looks at a stationary over the equator from the same over the ground point. And geostationary satellite useful majorly to cover wide areas. Many meteorological and communication satellites are geosynchronous types. And you are all aware that Clark theory of putting 3 satellites at 120 degrees separation, we'll be able to cover the full globe. That is how it is the theory that the aspect is being projected, studied, and implemented by many people. Now coming to sun synchronous orbits, now this is one important type of orbit which is used for our imaging applications, optical imaging majorly. Orbital plane motion is synchronous with the sun's apparent motion around Earth. Actually, sun motion is around 1 degree per day, and we maintain a constant angle between the orbital plane and sun vector. So maintaining near constant sun illumination for ground imaging means what? When the imaging is being done on any day of it, and at that time, the sun illumination at that ground point is almost constant. So the imaging, when we say constant illumination also is there with respect to the sun, and sun is illuminating the Earth, which is seen by the Earth, the satellite. So this is how the sun synchronous orbits are categorized for us. Then now I want to tell you, because first I should have told about orbit, but I have done other way, because I want to first give the applications and types of orbits. Now how the orbit representation is done as a 6 orbital elements. This is one way of representing, like semi-major axis, eccentricity, inclination, right axis of the node, augmentative energy, and true anomaly. These are 6 parameters which define the orbital plane, orientation, and these things. So when you say here, you can see that argument of omega is nothing but argument of the angle between the ascending node and the orbit's point of closest approach to Earth is a perigee. Then true anomaly in degrees, the angle between perigee and vehicle in the orbital plane. So what we are trying to tell is, using the semi-imaginary axis, all the 6 elements in orbital plane can be defined for any SSPO orbit, sun-synchronous orbit or inclined orbits, and we can understand where is the satellite in the orbit. That's what we are planning to do here. So this is how, if you see the ground trace, when the satellite is moving over the Earth, we can see the point of intersections on the Earth surface. These are locus of the points, and this is typical ground trace of the satellite moves. So this is, if you take the northern side, this is from north to south, this is descending. Similarly, you have ascending also when the satellite moves from south to north. So this is simple ground trace for us. Now coming to geosynchronous and Molyneux type of orbit tracks. G-orbit track is a point where you can see the G-orbit track is a closed orbit. Molyneux orbit track hovers over the northern latitudes for most of them at one of the 2 longitudes. That's what I told you. So the pink one, you can see that is hovering at 2 longitudes. These are our regions follow normally. Then you can see here, as I told, ascending and descending, both are there. The traces which are coming from north to south are descending, and which are going from bottom to top are ascending. So this is how the a typical low sun-synchronous orbit ground tracks move. And coming to the, sorry, I am audible, sir? Sorry. Hello?
Yes, sir. Audible. Go ahead.
Yeah. Okay, now coming to this now point is with respect to imaging. You see that a satellite is there, and we are trying to cover that Earth. Now what happens is, the band what you are seeing is that nothing but with respect to the satellite motion in the perpendicular direction, the swath is defined. So every satellite with the swath is defined based on the type of the payload, how many pixels are there, how much is the orbit height it is there, how many pixel, how many meters, and how much across track is spreading. So this is how the swath of the payload is defined. So this is what generally we it can be from few tens to hundreds of kilometers wide. This swath can vary. So you can see here the satellite is coming from when it is descending. You can see how the satellite is coming in the along track motion. In this, when the satellite was passing through over the region of interest, it has first imaged. Then next it has moved. This is along track motion. It has imaged next region. So it's a push broom technique. What is happening, and it is trying to cover the full region of interest. What we formed, what we are interested. But perpendicular thing, you can see the swath, how it is there. The swath is going to be covering the region. So now this is what is covered in one pass. The next path when it comes, then another region is covered. So like this, what happens is the full Indian region, based on the path pattern of the satellite, what is chosen for that orbital height and data, this region will be covered, and we'll tell sometimes the satellite covers this region in some n number of days based on the swath of the payload. So this is how the relation between, and at the same time, the illumination sun is maintained constant angle. So you will have the illumination also effectively. So you will get the good image resolution also with respect to optical payloads because of this constraint when it is applied. Now another thing is important point is the visibility. See, now the point is the satellite is moving the orbit. So when it is possible to communicate with the satellite is when the satellite is above the orbital plane. Means what you can see that if the satellite is this side, means in the other side we cannot communicate. But if you put the plane, if the satellite has to come above the local tangent plane, then only we can communicate. So this is what is the elevation concept applied. And normally for our telemetry and telecommand applications for the any satellite, we apply at least 2 degrees of elevation. Satellite has to move above this plane by 2 degrees. Then our TTC will apply. And for payload data download, we use around 5 degree of elevation. 5 to 5 degree elevation, we download the data. And 2 degrees to 2 degrees, we'll do the TTC operation. So this is how the radio contact with that station is done for monitoring both satellite health and collecting data from satellites. Advanced knowledge will appear in the, that's what then this is when we apply this constraint, we try to compute the station visibilities with respect to the particular satellite. And once visibility is available with the satellite, our ground station starts tracking, and we do this required mission operations with respect to that. So this is another typical visibility of IIRS orbit. You can see here the different ground stations, how when it is moving, and you can see here when satellite is here, it is able to communicate with this ground station. When the satellite comes towards here, this distance will use, or else here it is another station. This is how the ground stations variation normally are taken to support the satellite operations. So one now as this glimpse of all the things will tell you that how the satellite your objective were to the mission operations till it includes orbit selection, payload operation, data downloading, and end of life, how the disposal of the mission happens. So here now few more things I want to bring here. One thing is with respect to when you say any satellite, take an example of a satellite which is having covering the globe around 2 days. If somebody asks me to cover a satellite to cover the globe within 2 days, then what happens is how it is calculated. We know that Earth circumference around that is 2 pi r is around 40,000 kilometers. If the swath of the payload is around 1440 kilometers, you can see that around 29 orbits are required approximately to cover the whole globe. Means what? I'm able to. This is at equator. At higher latitudes, this improves significantly. At equator only, this we have to see the worst case thing coverage wise. So like this, we based on the objective of the payload and the swath of the payload, what is defined, we will try to select a particular orbit for that, and that is called the Q factor. That is Q factor is nothing but now it has 3 components in that. One is the number of days it takes to cover the globe, and the how many parts it shifts after every day. So this is how it is called. Like somebody says 14 1/2 means 14 1/2 means it is 29 orbits in 2 days. So one path shift in every day. So that's what 14 orbits. 14 is nothing but the number of orbits or 14.5 orbits it takes in in revolutions in 1 day. That's how the Q factor for the satellite, a typical example I told you. This will vary from satellite to satellite. We have multiple Q factors, but all this orbit selection happens with respect to the objective of the mission. So I think I have covered. I think more time I want to give for questions. Anything else you want to ask me? You can go ahead, sir. Sir?
Yeah.
I want to give more time for interaction, sir. Then.
Yeah, okay. Yeah, thank you very much for completing in record time.
So you told me 30 minutes, so I had to complete 30 minutes.
Yeah, thank you.
Any queries?
See what questions are there.
Yeah.
To upload. Yeah. In the meanwhile, I will ask one question.
Yes, sir.
For covering tropical region, we need inclination of around 30 degree or 25 degree like that, isn't it?
That's sir. Megatropics, yes, 22. Yeah.
Yeah, megatropics.
Yeah, tell me, sir. Hello?
So, for studying tropical meteorology and tropical atmosphere, we need more satellites like megatropics and in that kind of orbit. So, yes, is it any difficult compared to other orbits, maintaining those?
Sir, maintaining the orbit is not a problem, sir, because our material, if when you say 20 degree, okay, example we take megatropics, which is 20 degree inclined orbit, 25 degree inclined orbit, and orbit height is around, I think, around 780 or around 800 kilometer orbit. So with single satellite, what happens is tropics will be able to cover within the repeat cycle, as I told, megatropics is repeat cycle, which will be able to cover the full band. Okay, I'll explain you another way, sir. 1 second. Sir, example that you assume that tropics are plus minus 22 degrees only you want to cover, sir. Normally. Yeah, so what happens is this 25 degrees band. This band you can, this now I have taken plus minus 82, but you can take this yellow color band, which is it shrinks to plus minus 22 degrees. So yes, with respect to the thing is, if I tell that I want to cover this tropics within how many days, whether you want every what's called what time, number of days you want to cover.
Was roughly revisit time was 7 days or something like
7 days. That's what. If you say that I want, means single satellite is giving 7 days. Correct, sir.
No, if I want to cover, my question was whether it is easier to operate polar orbiting satellites or this kind of which
sir,
one is?
Sir, there is. I don't see any difficulty, sir. Only thing is with respect to our momentum management. When we use manual torquers, that field strength is minimal when you come close to equator. So torquer capacity and disturbance are slightly different. That is only major difference which comes for you. And as being inclined orbit, your sun motion happens continuously with respect to thing. So that we should have panel solar array mounted in such a way that we have powering generation all the time. And that is what is the few complexities are there with respect to sun signals versus inclined, but still we will be able to manage the mission, sir. Not an issue.
Okay. Now let us see the students' questions.
Yeah, yes, sir.
So one question is, why do satellites at higher altitudes stay in orbit longer than those in lower orbit?
Yeah, okay, very good question, sir. Sir, what happens is when the example will take a case, if a satellite is in an orbit of 300 kilometers orbit altitude and another satellite is in an altitude 720 kilometers, the basic difference what happens is the drag effect which comes on the satellite because of the lower altitude. One is the aerodynamic drag when plays a critical role. And the disturbance is secular, so the decay of the orbit, if you are to maintain a frequent maintenance of the orbit is required for a satellite which is in lower altitude, but when you are in higher altitude the decay is minimal, so the drag effect is minimal, so decay is also slower. So time what the satellites higher altitudes give you more time than the lower satellites, altitude satellites. If you want to keep the get more mission life in the lower orbit satellites, lower altitude satellite, you should have frequent stage orbit keeping orbit maintenance maneuvers, so that altitude is maintained and we are able to get the required objectives. Only fuel is a penalty because of drag effects. Otherwise, decay will happen very fast.
So one more question. Why
Yeah.
are Molniya orbits preferred for communication
Okay,
in high
sir.
latitude regions compared to geostationary orbit?
Yeah, sir. But because the Molniya orbit's critical inclination 63.5, you say take their what's called their epsilon line rotation is almost constant, and they'll put apogee around some 20,000 kilometers or 30,000 kilometers above that point. So that apogee point, when the satellite velocity is lower, it will be able to see the same region what it is there. So with single satellite, we cannot get, but two satellites, when you put in the same plane, we'll be able to give it almost satellite motion will takes care of that. So one satellite, when it is coming towards perigee, other satellite comes to apogee. So we'll be able to get both the using both the satellites the required objective of communicating with the Earth. So that's why people higher latitude prefer.
Okay, next question. During the Aditya L1 mission planning, what were the key challenges in selecting the L1 orbits?
Yes, sir. Sir, one thing is when you say the first point is Aditya Sun Earth L1. That was our before that the point what I want to say is our payloads when they are monitoring the sun, they have to be before this a satellite proposed before Aditya L1 came, Sun Earth L1 satellite came. A satellite was proposed in low Earth orbit and the eclipse should be 0. That's what was the requirement, so that our payload will see the sun continuously. But when you are in the Earth in planes, the manosphere effect is there. So you cannot clearly distinguish the effects because the effect of magnetic field, manosphere effects are there in the payload observation. So with respect to the key observations, what we did is first thing, as we are going to first time to the Sun Earth L1 point, the trajectory to reach that point itself was a complex thing for us. And once we build that reaching the trajectory to reaching the satellite to Earth L1, maintaining the orbit is another criticality, as well as because we are not having any experience about this, how the satellite will, once we put a satellite to Sun Earth L1, we don't have an experience how the satellite will undergo perturbations like solar radiation pressure, how the orbit has to be maintained. And one more thing is the communication from satellite to ground, as well as your because you have to have one thing called sun exclusion zone, because you are directly observing the sun here always, and there is no eclipse at this point. So what happens is the communication with Earth is always possible. So the advantage is that you are able to have observation as well as communication. But criticalities wise, you see, the reaching the Earth L1 was most critical for us, and maintaining the orbit and operating the payloads is more complex for us. These are the criticalities which you see. with respect to this thing. These are the criticalities, sir, which we faced.
Yes, yes, yes. And one more
And mission
question.
operations, we don't have any experience about managing the mission.
Yeah, I
So that
understand.
also we
It
got
is,
a
mostly relied on probably theoretical this thing only.
yeah, correct, sir, correct, sir. Now we have good hands-on experience because almost the 5th halo orbit is going on. So we are able to get good understanding of the mission now, and we are able to operate all payloads also now at this point.
Okay, one more question. For the
Yes, sir.
Gaganyaan mission, which of the 6 orbital elements will have the toughest tolerance at insertion? And what is the consequence if the element is off by even a small margin during the crewed operation?
Sir, I think this question we can skip, sir. Don't mind.
Okay, okay. And then one more question is there that is more related to geomagnetism.
Okay.
He is asking why Earth magnetic pole is never still, it is continuously shifting like torque. That,
Okay, this our Srikant
I
can
guess
explain
the
better way.
best answer
Srikant,
is we are only observing that shift.
yeah, correct.
That reason I think nobody
Yeah.
no one is able to tell.
That is happening it will happen, flip will happen once in some years. Sometime it will happen.
Inside geodynamics,
Correct. Yes, sir.
geodynamo, how it is working, it is only
Correct.
theory only. We don't know.
Correct, sir.
Yes, sir. With this, we have completed all the questions, I guess. All the
Yes, sir.
students'
Thank you,
questions.
sir. Thank you, sir.
Thank you very much for your
Thank you, sir.
interaction and talk. And
Yes, sir.
I
Thank you, sir.
thank all the students and coordinators who have participated in this,
Yes, sir.
listening to this
Thank you.
talks.
Yes, sir. Thank you, sir. Thank you all. Thank you, sir.
Now over to IIRS.